It's a great pleasure to be here today. It's a great pleasure to see the support for climate science and the interest in climate science by the Simons Foundation. This is the year of Mathematics for Planet Earth, and this combination of climate science and mathematics with climate science, I think, is a quite exciting area. Today I'm going to try to give I don't really know who I'm talking to, so it's always hard to prepare a lecture when you don't really know who your audience is, and so we'll see how I do, but I'm assuming that you aren't atmospheric scientists, and if you are, some of you I know are, then hopefully you'll just enjoy some of the relief of a different view, a general overview of the climate system. This is a painting by a guy named Ivan Aivazovsky. He was, according to Wikipedia, one of the great seascape painters of the 19th century. And it's actually a painting of the eve of the second day. So it's from Genesis. And in Genesis, before the second day, the statement is God separated water from water to create the sky. And I find that fascinating. And the idea that in this early creation story that sky was associated with water. Often when you think about atmospheric dynamics, we think of the sky as everything but water, and then a long time later people add water back into the system. But for the creation, sky and water was synonymous. There was this hydrosphere below the oceans and the hydrosphere above the sky. And so the defining quality of the sky was the water in the sky. And so if you remember anything from this lecture, I'm going to try to convince you of maybe two things. That almost everything, and I said this in my abstract, almost everything that we know and understand about the atmosphere, climate, and climate change has to do with our understanding of water in the climate system. And almost everything that we don't understand about the atmosphere, climate, and climate change has to do with our lack of understanding of water in the climate system. So the fact that this separation of water from water to create the sky signifies the importance of water is also symbolic for what we think of climate as a whole in terms of the effect of water on the climate system. And it's even more surprising because if you took all of the water out of the sky and condensed it, brought it to the surface of the Earth and condensed that water, you'd have about 2.5 centimeters, a good inch, of water spread around the surface of the Earth. So all of the water in the sky amounts to an inch, a global puddle, if you like. If you compare that to the oceans and the ice reservoirs, they contain about 100,000 times as much water. And if you work that through the exchange rates of water between the ocean and the atmosphere, and you ask yourself how long does a water molecule get to be in the sky, you come up with the answer that every 3,000 years or so, a water molecule gets to make a little sojourn into the atmosphere, where it spends a week before meeting its colleagues and coming back to Earth in a downpour. And in that week, it really changes the world as we know it, because the atmosphere without water is really unimaginable as the atmosphere. And they even knew it when they were talking about creation. So when you think of these hydrosphere above and hydrosphere below, the hydrosphere below, we know, the oceans, we see them here, and we can see them looking down from space at our planet. So this is from Meteosat, a geostationary satellite from the European Space Agency, which looks down. It's a weather satellite. And when you look down, what you see mostly is this dark color here. It's the great absorbing oceans, and you're looking down at a wavelength in the visible part of the spectrum of light. So about 0.5 micron is the wavelength of light in the visible spectrum, say 0.6 microns. And we see down to the surface, and the dark means all the energy in these visible wavelengths are reaching the surface, mostly being absorbed. Here, false color being reflected off the land surface. And you see a hint of the hydrosphere above the water in the sky through the clouds spread out through the climate system. But mostly all of us know the ocean below. Few of us really actually see this ocean above. And if I can remember where to... There. This is all we have to do is we have to go back to outer space and we have to look back at the planet and change our glasses, well, put on infrared glasses. Instead of looking at a wavelength that's about 0.5 micron, increase that by a factor of 10 to 6 microns, and we look at the Earth and this is what we see. And it's a real tempest of a planet, big swarms of what seem like gas. It looks like a gas giant. It doesn't look like Earth. We don't see the surface, and unless you're a student of the atmosphere, you wouldn't really know where you are on this if you're a student of the atmosphere, you'd see the swirling motions which are going around the poles. You'd see the broad vapor in the tropics. You'd see that this explosion here of little white speckles, which are very deep convective clouds, are happening during the daytime over the Amazon, and Africa is hidden behind here. But looking down from above, you don't see the surface because you're seeing the hydrosphere, the water above, not the water below, when you look at the infrared. And I think that the important point I want to make here is that the mighty water molecule makes the atmosphere opaque in the infrared, and that's a really defining quality of the atmosphere. And it's a defining quality because of special properties of water. Right? This lecture I'm giving today is going to be printed in physics today in about a month or two, and it's water in the atmosphere. And one of the things when I was preparing that lecture was really trying to appreciate the power of what I call the mighty water molecule. And if you look at the mighty water molecule, it's here, blown up for you. That's a picometer. So, across here we're talking about some tenths of a nanometer. So small like a molecule. It's a small molecule like most of the molecules that make up the planetary atmosphere. But it's a very unusual small molecule because it has oxygen in it. So this would be the oxygen. These would be the two hydrogens. And the unusual thing about it is, one, that it's asymmetric. So if you imagine I'm the water molecule, then my hands would be the hydrogens and my head would be the oxygen. And so a lot of molecules would be quite symmetric, like CO2 would be symmetric. And methane is relatively symmetric. O2 and N2, the diatomic molecules, are symmetric. And water is very unusual because it's asymmetric, and it's also unusual because it has oxygen. Oxygen is one of the most electronegative elements, which means it's an electron lover of all the elements. And because it's an electron lover, it kind of holds on to its electrons, which leads to a fairly big charge separation. The charge separation gives water a strong dipole moment. And the asymmetry give it interesting moments of inertia. And so this combination of a strong dipole moment and its asymmetry in the sense of its different moments of inertia give it a very rich appetite for infrared radiation. So if you look at simple molecules, the way they interact with electromagnetic radiation is that they tend to rotate. You have your quantum rotational states, which take low wavelength radiation. They tend to vibrate, which takes medium energy radiation. And then you'll have electron transitions, which will take very high energy radiation. But in terms of the Earth's radiation budget, what's really important is this combination of an ability of a model to rotate, for which you want a dipole moment. If you rotate and you have a dipole moment, you're very good at absorbing and emitting energy. And vibrating also. And you can see that a little bit if you actually look at the spectrum of radiation. So now I'm going to tell you a little bit about how this water molecule, which covers the atmosphere from above, how it influences the radiant transfer of energy between the Earth and space. And here in this diagram, what I've shown is a spectrum. So this would be a wavelength of light. And we're starting here from a few tenths of a micrometer to a few tens of a micrometer. And the same scale is up here. And at first, I just draw two normalized blackbody radiation curves. And the first one shows the blackbody radiation you would get from something like the sun, emitting blackbody radiation at a sun-like temperature of about 6,000 Kelvin. And it peaks here where visible light peaks, where our eyes are sensitive, at some, say, 0.5, 0.6 microns. And this is where the Earth gets its energy from the sun, from this sort of spectrum. The Earth warms up and it emits energy back to come into balance. So it's a sort of a forced equilibrium system. It's getting energy from the sun and it's emitting energy back, and it comes into equilibrium. And it does that by emitting energy at a different wavelength. At its temperature, terrestrial radiation, it emits at about a temperature about 20 times colder than the sun. Instead of 6,000 K, it's 300 K. And by Wien's law, then you expect the peak of the spectrum to be about 20 times longer in terms of the wavelength. So the Earth radiates energy, terrestrial radiation, at a wavelength at about 10 microns. And water virtually dances in this splendor of radiation that you find in the infrared. Unlike any other molecule, its ability, and that's shown here, these are absorption lines, discrete absorption lines, from rotational modes of the molecule. So you imagine me, I'm the water molecule, and I have a strong dipole moment, and I go through my quantum rotational modes here, and you get this very, very rich rotational spectra from the water molecule. But you also get these vibrational modes, and there's three fundamental vibrational modes. There's one which is the two hydrogen atoms going like this, a bending mode. And then there's a symmetric stretching mode, the water molecule like this. And then there's an asymmetric stretching mode, which goes like that. And these ones are here, and you can see the rich spectrum, and they get ornamented because they combine with the rotational modes. So water doesn't just wiggle, but it rotates. And this gives it this very rich and broad spectrum. So when you think about greenhouse warming in the future, what you should really think about, that's the other thing you could remember, is you can imagine water molecules doing this when they get warm. And that my children know this dance. This is the greenhouse dance. You just do like this. This is the water molecule. This actually lambda 2, the second fundamental rotational vibrational mode. And the wealth of these lines here is what makes it so effective at interacting with radiation across the infrared. From the near infrared, where there's still sunlight, these overtones of the fundamental modes here, as they die down as you go towards visible, make water actually the most important absorber of sunlight as well. But far more important is water's ability through here to make the atmosphere opaque to infrared radiation. One of the things you don't see here is there's thousands and thousands of discrete lines associated with emission absorption of water vapor at that wavelength. But the lines aren't really straight. So if you look at a real emission line, instead of being just a discrete line, of course, through collisions and Doppler shifts, a line that doesn't look like this, but it has some shape. And so if you have lots of lines, this is called the wings of the line, and these are the far wings of the line. If you have such a surfeit of absorption features, the far wings overlap, so that in between, not shown here, is you have something called continuum absorption, where you absorb just not on the line, but off the line. And the more lines you have, the more continuum absorption you have. So the whole point of this picture is to convince you that water is a virtuoso in terms of its ability to deal with infrared radiation. There's no other molecule that really even comes close. And that helps us understand, this will be a very quick lesson on the greenhouse effect. And I'm going to give you a really quick lesson on the greenhouse effect for two reasons. It'll help me explain things in the latter part of the lecture where I say how understanding of water helps us understand climate change. And the other reason I want to give you a quick lesson on the greenhouse effect is that most people learn the greenhouse effect in what seems to be a rather strange way, and it's much simpler to understand if you learn it the right way. So I'll try in 2 minutes to explain it to you, to people who don't know it in the right way. So here again, we're looking down at the planet from space with our infrared glasses. And this is what the temperature structure of the atmosphere looks like in the red line. So imagine this is temperature going to the right, and this is depth in the atmosphere, so we're at the surface here, and the top of the tropopause here. And if you just measure how the temperature is in the atmosphere, and we'll get to why this is later, but the atmosphere is a stratified fluid in the sense that the temperature decreases with height through the troposphere. So that's what this red line is showing. So that the change in temperature with height, which I donate gamma here, is approximately this gamma m we'll get back to, but it decreases with height. As you look down at the Earth, what you see is you don't see to the surface, you see to some effective height, say here, because the atmosphere is opaque. This is an equivalent height and an equivalent emission height. And if you think of the system coming into equilibrium, it's getting radiant energy. Remember, the atmosphere is transparent to visible radiation. That's why we can see the continents and the ocean in that initial slide. It's getting all that energy, it's absorbing it. So to be in equilibrium, it has to radiate as much energy as it receives. But on average, it's radiating from a depth about this deep at a temperature that's whatever the temperature is here. So the temperature here has to be warm enough so that radiation from this level equals the input of solar radiation from the top of the atmosphere. You can ignore this for now. This is just the water profile, which raises the emission height to something above the surface. So the atmosphere is opaque. So how does the greenhouse effect work? It just makes the atmosphere more opaque if you add more greenhouse gases. If you add more infrared opacity to the atmosphere, instead of being able to see all the way down to the atmosphere to this height here, you can't see quite as far, and you'd see to a height maybe here. But now you have this problem, because as the atmosphere becomes infrared more opaque, you don't see as deep into the atmosphere, and the fluid is stratified. So you're actually seeing to a level which is colder than the level it was at before. And if it's colder, it's not emitting as much radiation. So you're out of balance. And so the system has to come into equilibrium by warming, so that at the new emission height, when you make it more opaque, at the new emission height up here, the atmosphere will warm until it gets the temperature it had at the old emission height when it was in equilibrium. So really one way of thinking about the greenhouse effect, and it's important that you think about the greenhouse effect looking down at the atmosphere from above, because otherwise you get all confused about absorption lines being filled and bands being filled and all of this nonsense. And the whole point is this question, you're looking from outer space, and how deep do you see into the planetary atmosphere? And what is the temperature there? And as you increase the opacity, what you have to do, because the fluid is stratified, you move up, it's a colder temperature, so you have to warm the whole fluid to come back into equilibrium. And water is fundamentally what gives the atmosphere this infrared opacity. Not only is water vapor important to the structure of the radiant balances of energy in the atmosphere, but also condensed water. So one of the interesting things about water is that it goes through its various phases in the atmosphere. So that Earth happens to be at a point where water can visit its different phases, and you have this water cycle. And here's the water molecule over here at a few fractions of a nanometer, and this is again scale of the object. And here I draw common hydrometers, or condensed matter, condensed water in the atmosphere. And you have condensate, all of this would be condensate, condensed phases, precipitate, some of them are big enough that they precipitate, and others tend to be more suspended. So if you look here at the dividing line, I said things which are about this, which are smaller than about 100 microns, tend to be fairly effectively suspended in the atmosphere. And this is just a terminal velocity balance. So it turns out that particles in the atmosphere, if you put a drop in the atmosphere, its fall velocity in this regime goes about as its size squared. And so if you work things out, you'll find that a 100 micron drizzle drop falls at a speed of about 3.5 centimeters per second. So it doesn't fall very fast, about 3 centimeters a second. And so things that are smaller than 100 micron are falling a lot less rapidly. They're more or less suspended in the atmosphere. They're small. And things which are bigger than 100 microns fall quite a bit faster. So a snowflake falls at about half a meter a second. Big raindrops will fall up to almost 10 meters a second, and graupel and hail will fall also faster. So these are fairly rare because they're big, and they don't live in the atmosphere very long, because as soon as they get this big, they fall right out. Whereas these ones will follow the atmospheric flow, and they're more controlled by whether or not they become big and fall out of the atmosphere, or whether the thermodynamic conditions which led to them forming change, and then they stop being condensate and vaporize back into the vapor phase. What's interesting is the laws in which the ways these things interact with radiation. It's a bit different than the way this works, but it's also something we understand for more than 100 years. I think for me scattering is about 100 years old right now. And what you can work out is that if the wavelengths are quite small compared to the size of the object here, so the visible wavelengths, which are in this range here, the objects are very good at scattering the radiation. So they mostly scatter. Whereas when the wavelength gets to be on the same order as the object, so here the cloud droplets, an average cloud drop might be 10 microns, the particles are much more effective at absorbing. So the interesting thing about condensate in the atmosphere is that it scatters solar radiation and it absorbs terrestrial radiation. And it's mostly these, because a lot of surface area is in the suspended phase, cloud droplets, and they scatter radiation very effectively. I mean, these are the clouds. And so this means that clouds affect the visible stream of radiation by scattering and the terrestrial stream of radiation by absorption. So if you look at how that works, you go back to our two pictures of the hydrosphere above and the hydrosphere below, and here these clouds are very opaque in the IR. So you don't see any further than the cloud top. That's why I said these are the tops of deep cumulus clouds. And so they make, underneath the clouds, the atmosphere is especially opaque. You're not seeing very deep at all here. But they're also, this is 2 different days, so don't try to match this figure with this figure. But the clouds here are reflecting a lot of sunlight. So clouds in the atmosphere, they have a greenhouse effect, like that of water vapor that I showed. But they also have an albedo effect, because they interact with visible radiation in a way that's quite strong. So clouds, on one hand, through their greenhouse effect, they tend to warm the planet, warm the surface. And through their albedo effect, they tend to cool the surface. And you can put that together. If I find my pointer, you can put that together, and you can say, how do clouds mediate the flow of energy, and how does that help us understand what the structure of the climate system is? And what you find here, and what I've drawn, is you imagine the solar radiation coming in, and a balance at the top of the atmosphere. You have to say as much radiance comes in, radiative energy is radiated into the system, as is radiated out in equilibrium. So think of these as sort of one unit of energy coming in, 1 unit of energy has to go out. That's equilibrium. It comes in as in short wavelengths of solar radiance, and it leaves in the long wavelengths of terrestrial radiance. The solar radiation mostly gets all the way to the surface. The atmosphere is fairly transparent, so 75 or 74% of the solar radiation reaches the surface. But when you think of the surface, the warm surface trying to radiate its energy back out, you see that of the energy that eventually leaves the system, only about 26% by this calculation actually originates at the surface. So there's a very strong flux divergence of thermal radiation between the surface and the top of the atmosphere in the thermal infrared. That's not really compensated by the convergence of the solar irradiance. So, 26% of the energy that comes in is absorbed, but here you have a divergence of 75%. So the atmosphere, because of its greenhouse effect, because of the effect of water, is cooling. It's radiating energy away to space. And this would lead to an atmosphere which is unsustainable. It would keep cooling and cooling because the atmosphere is losing energy. So something has to balance it. And the way the system balances this radiant loss of energy to space is through enthalpy transport from the surface, so evaporation. So evaporation, you evaporate water vapor from the surface, it cools the surface, but it condenses in the atmosphere, and the condensation returns to the surface as precipitation. So this is the water molecule's 1 week of fame. I always think of Andy Warhol when I think of water molecule, because I always have that 15 minutes of fame, and if you kind of work it out, 15 minutes in a life of 70 years, it's not so far off from a water molecule getting to spend a week in the atmosphere for once every 3,000 years. So the water molecule's 15 minutes of fame is coming about, and this is an interesting point, it's coming about because the water is radiatively active, it has to rain. So it's a funny phrase. I'm saying water makes it necessary to rain. And he said, of course, you need water to rain. But it's not that the water is necessary to form raindrops. It's the rain is necessary to balance the radiative flux divergence, which is caused by water. So the radiative effect of water drives the hydrological cycle. Just by understanding those funny diagrams with all those peaks that I showed in the beginning, the absorption spectra of water vapor, we can tell you how much it will rain because it's really controlled by water's radiative properties. And you can show that. We did a calculation. These are based on calculations from a model, but you can do it looking at satellite data and measurements at the surface. I mean, there's no mystery. It's just all based on radiative transfer of water molecules. And you can play a game with the model, though, is you can say, let's let the water be transparent to radiation. So we won't let the clouds have any radiative effect, and we won't let the water vapor have any radiative effect. And you can ask what happens. And that's what happens here. So now what happens if the atmosphere is transparent to water, almost all of the solar radiation comes down to the surface. Here, all but 7% comes down. And almost all of the radiation that leaves the top of the atmosphere originates at the surface, which makes sense because the atmosphere is more or less transparent, not only to visible radiation, which it was to begin with for the most part, but also to infrared radiation. And what you now have is you have an atmosphere that's in radiative equilibrium, whereas here it was in radiative convective equilibrium. You needed evaporation to balance the heat budget of the atmosphere. The evaporation led to deep cumulus clouds, condensation, and precipitation. That balanced the heat deficit from this thermal flux divergence. Here you don't have it. So if you take away the radiative effects of water, it doesn't rain. The atmosphere goes into a relative state of stasis. And of course, the surface is much cooler. If you add up the different effects of water, the greenhouse effect of water leads to about a warming of 40 Kelvin. And then the condensate contributes additional warming through the cloud greenhouse effect and additional cooling and compensating cooling through the cloud albedo effect. It turns that clouds as a whole act to cool the planet, so that 40 degrees of warming that I mentioned from the water vapor greenhouse effect is offset by about a factor of 1/2 from the net albedo effect of clouds. So the fact that the clouds are a little bit better at scattering solar radiation than they are at absorbing infrared radiation means that clouds work against the water vapor greenhouse effect as a whole and cool the system. But overall, the water vapor greenhouse effect is the dominant thing. So if you get rid of the effects of water on radiation entirely, both from clouds and from water vapor, instead of having a temperature of 300 Kelvin at the surface, you would have a temperature of 280 Kelvin. So all I explained now to you was the radiative effects of water. There's nothing mysterious. I mean, we understand a lot about the atmosphere just because we understand water spectroscopy, just because we can do radiative transfer. It's all old physics. It's well understood and explains really a lot about the surface temperature, about how much it will rain, and how surface temperature will change. The thing that's really interesting about water isn't just its radiative properties, so it's also its thermodynamic properties. And water is a greenhouse gas, but so is CO2. the difference between water and CO2 is that water is very, very strongly coupled to temperature. And I'm going to show that to you here by this. I think if I had to make a case for there being one equation that's more important than any other equation in climate science and the atmospheric sciences, it would be this. This is the Clapeyron equation. Some people call it the ClausiusClapeyron equation. It's a direct consequence of the second law of thermodynamics. This is a thermodynamic factor that comes from the physiochemical properties of water, beta, temperature, and this is temperature here. So it's a relationship between how much water you would have in saturation between a condensate and a vapor phase, E sub S, and temperature. So this you can derive, and you do it in every sort of undergraduate thermodynamics class. It's 19th century physics. It's nothing surprising, but it provides an enormous constraint on how water vapor, which is so important to the radiative budget of the atmosphere, it provides a very strong constraint between this and temperature. And you can see that here in this diagram. What this diagram is, it's temperature on this axis and vapor pressure on this axis. And what I did was I went to big archives of weather data, and I said, let's take a particular pressure level. Here, say 900 millibars, so somewhere near the surface, 500 meters to a kilometer above the surface. And let's get at every point around the globe the vapor pressure. Let's measure it, and let's bin it. Let's group it by temperature. So everywhere where the temperature was, say, 295 Kelvin, then I said, what's the vapor pressure on average here? And I get this dot, and this line is sort of the range of the values. So what it shows you is that on that pressure surface, that 900 millibar or hectopascal pressure surface near the surface of the Earth, that whenever it's 290 Kelvin, on average the vapor pressure is this value, and there's a range like this. And then you can take a slightly colder temperature on that same pressure level, and you get all of these guys. And it doesn't really get that cold near the surface of the Earth. If you want to get colder air, you have to go higher. So you go to the next pressure level, and you get the blue ones. And eventually you end up here in the upper troposphere, sort of maybe 7 or 8 kilometers above the surface in these red ones. And then you get airline flight cold temperatures. When you fly in the airline, it says it's minus 60 degrees Celsius when you're up there at the top of the atmosphere. That's here. And if you measure the vapor pressure there, you get these values down here. And what this black line is this. So this is the theoretical prediction, and it tells you, of course, that the atmosphere is actually very close to saturation on average. This varies over an enormous magnitude, 4 orders of magnitude. But this ClausiusClapeyron, or the Clapeyron equation, provides a very strong constraint on the amount of vapor in the atmosphere. And that's easy to understand, right? Because if you try to cross this line, what happens? If you put vapor, if you are at this temperature and you have too much vapor, then you're supersaturated. If you're supersaturated, you condense water into the condensate phase. The condensate phase forms precipitate and it falls out of the atmosphere. So that the atmosphere is very efficient at removing water if you have a vapor pressure that's too large. So this is an enormous constraint on how water is distributed in the atmosphere. But this is fascinating, right? Because we have a system where water is controlling temperature through the radiative effects. But thermodynamically, temperature is controlling water. And this coupling between water and temperature gives us an enormous lever in understanding how the climate system works. So this is one constraint, how temperature controls water. And we're going to follow this constraint. And here I'm just going to be a little bit more cursory. And you can ask another thermodynamic relationship, and this is called this lapse rate law. So a lapse rate is how a temperature changes when you displace something adiabatically. So imagine you have a parcel of air, a balloon or something like this, and you displace it adiabatically. Adiabatically means we don't add any heat to it. So there's no heat exchange with the environment. And if we move air upwards in an atmosphere, what happens? We're moving it to lower pressure. If we move it to lower pressure, that means it expands. It does work on the atmosphere. And then you have to get that energy by conservation of energy from somewhere. And that happens as you move air upwards, it cools. So expansional cooling. We all know that when we let the air out of our tires or our neighbor's tires or whatever we do. And this gives us the adiabatic lapse rate. Now, so I wrote it here for dry or unsaturated air. The adiabatic lapse rate has a value which is about every second grader or maybe fifth grader, I don't know, learns. Not in this formula, but if you lift air 1 kilometer, it cools off by 10 Kelvin. So this is this adiabatic lapse rate. What happens if the air is saturated, of course, is you have another reservoir of energy. You just don't get it from the thermal energy of the molecules, but you can transfer energy because the enthalpy of vapor is higher than the enthalpy of condensate. So as you lift air and it cools and condenses condensate, water condensate, you release, in a sense, latent heat. You have an enthalpy exchange from the vapor to the condensate phase. And that means that you don't cool as much. So you get this additional factor, which you can work out again in your undergraduate thermodynamics class. And this thing is a number that's less than 1. It depends on temperature. And in the atmosphere, it will assume values as low as about 0.4. So what you find is that this, what you would call the saturated lapse rate, comes from thermodynamic principles. It's related to this Clapeyron equation. That was the famous beta that I had in the last relation. And it tells you that saturated air cools off adiabatically less rapidly than unsaturated air. In the atmosphere, this does something fascinating because it tells you that if, imagine your air and you're just saturated here, right here, it's just saturated, and you push it down, what's going to happen? It's going to warm up. So nothing's going to condense. It's going to follow this law. Just saturated air and you push it up. What's going to happen? It's going to cool off. It's going to condense. It's going to follow this rule. So in the atmosphere, you have this great thing that you have this asymmetry, this fundamental asymmetry between upward motion, which tends to want to follow this rule, and downward motion, which tends to want to follow this rule. And because this is the smaller of the two, the radiative cooling of the atmosphere destabilizes the atmosphere to moist convection. And moist convection tries to bring it back to neutral stability, which is equal to this theoretical prediction, the moist lapse rate. So just again, because of the properties of water, we can tell you a lot about the structure, especially in the tropical atmosphere, of the stratification. We can tell you how much temperature is decreasing with height through the troposphere. So again, this comes from basic understanding of how water, there's no mystery, there's no complicated model, there's just, sophomore thermodynamics, which tells you about the thermal structure of the atmosphere. And so if you put some of these things together, you can say, well, water tells you how much the surface temperature is because we know the greenhouse effect, we know the radiative effects of clouds. Water tells you that it has to rain because you have to have convection to balance the heat loss, the radiant loss of heat from the atmosphere. But if it's raining because you have these big convective currents. The convective currents are relaxing the atmosphere to a stratification which matches this moist adiabat. So we know something about this. The other thing we know that's really interesting about water is this. Why is the top of the troposphere up here at 15 kilometers? And the interesting thing, if you follow these arguments about how water works, is that as you go up, it gets colder and colder and colder. But because of the Clapeyron relationship, you get less and less and less water. So here I say, because of Clapeyron, we're always below the saturation humidity, because as soon as we go above, we precipitate water out. So we're always below, but this goes almost exponentially with temperature. So as temperature decreases, the saturation humidity decreases exponentially. So as we get colder and colder and colder, we can have less and less and less water. And eventually you get so cold that you have so little water in the atmosphere that it doesn't matter radiatively anymore. So the radiative impact of water just isn't there. And if the radiative impact isn't there, you're not destabilizing the troposphere by emission to space. And so essentially water acts like a thermostat on the temperature at the top of the troposphere. Because when the temperature is cold enough, it's telling you that you have little enough water that it really doesn't matter radiatively anymore. And you can think of the weather layer, the layer where you have mixing and clouds and convection, is really the layer in where water destabilizes the troposphere, especially in the tropics, because the tropics don't have complications from angular momentum, which Lorenzo can give you a lecture about, but not me. So understanding of water explains, I would say, the average surface temperature of the Earth. The strength of the hydrological cycle. If we understand the radiative properties of water, we can say how much it rains. It tells you about the depth of the troposphere, what we call the troposphere, this weather layer, this mixing layer. And it also tells you about its vertical structure, how the moisture profile is in the water. And another thing which I didn't explain, but you'll have to take my word for it, is that this asymmetry between the upward moving air, which follows the moist adiabat, this saturated adiabat, and the downward moving air, which follows the dry adiabat, constrains the relative size of the convecting zone. So if you look back on the planet, if I go back, just for fun, here, you see the areas, these little bands, it turns out, or here, this is better to see the really deep convective clouds. The area of these deep convective clouds is really quite small compared to the overall area of the surface. And this is because of the asymmetry between up and downward motion. That upward motion goes up very fast, following the moist adiabat and these narrow convective currents, and the downward motion is relatively gentle. So the fascinating thing is from water, water tells you a lot about the structure of the atmosphere. I haven't really talked about climate or climate change. Climate, you could say, is the average surface temperature. So the average property, there's a bit of climate, this is the climate as it is, but it really hasn't said much about how the climate would change. And that's what I'd like to do in the last 15 minutes or so, and then we can have some fun discussing water and questions, or going out and drinking water in the lobby, so to speak. So water not only explains these basic properties of the atmosphere, it also guides our thinking as how the Earth system, or the Earth as a whole, will respond to perturbations. And I'll try to convince you of this, building on the knowledge that we have now, and say, what do we really understand? And then at the end, I'll try to say what we don't understand because of what we don't understand about water. So if you took the climate system, and some of you are probably here at Brian Soden's lecture, and it was a lot about the first half of what I'm going to talk to you about today. And if you just take the normal structure of the atmosphere and you say, let's make the atmosphere more opaque by adding CO2. Forget about making it more opaque by adding water. We're going to add double the amount of CO2 or any other long-lived greenhouse gas which behaves independently of temperature. So we're going to make the atmosphere more opaque. And then we're going to ask what happens. Well, if it's more opaque, what happens is you're emitting from a higher height. The temperature is there is colder, so you're emitting less radiation. You're still getting the same amount of radiation in. So the system has to find a new equilibrium. It does that by warming up. And if you say the only thing that we're going to allow the system to do is change its temperature, nothing else is allowed to change, and you figure out what happens, what you'll get is that the temperature change from doubling CO2, so increasing the opacity of the atmosphere in an amount you would expect from doubling the amount of CO2, you'd get a pretty modest temperature change. You'd get a warming of about 1 degree Celsius for a doubling of CO2. So this is the sort of no water warming. But then you can say, why would you think like that? Because we know how important water is to the atmosphere as we know it, so who's going to say nothing else is going to change? Because we just showed you that wonderful curve about how water tracks temperature so beautifully. So you have in the back of your mind this figure here, maybe. And in the back of your mind, this figure, and we say, well, what do we know about water here in this figure? What else could change if we're warming? Well, if we're warming, for one, we expect, as the temperature here warms, the saturation humidity will increase exponentially, and we'd expect the humidity structure to follow that. So the best null hypothesis isn't that the absolute humidity would stay the same in a warming atmosphere. The null hypothesis really says that the relative humidity would stay the same. And so you can figure that out. You can say, well, we know from thermodynamics how much the saturation humidity would change. We'll assume the relative humidity is the same. We can calculate how much extra water vapor there'll be in the atmosphere. That's this water vapor feedback, which was the discussion of the last lecture. And you can just go through the radiative transfer and figure out how much this additional water vapor would make the atmosphere yet more opaque, causing yet more warming. It's a positive feedback, right? Because as you warm the atmosphere, it contains more water vapor. As it contains more water vapor, it becomes more opaque. As it's more opaque, it must become warmer. And so this is a vicious cycle, which is a positive feedback. There's also a negative feedback because the temperature structure of the atmosphere, remember we're going to warm it, the temperature structure here depends on, is governed by this lapse rate, gamma m. And again, we worked that out in sophomore thermodynamics, and we found that gamma m is actually a decreasing function of temperature. And so as you go to warmer temperatures, this curve here doesn't, it becomes straighter, so to speak. It doesn't keep the same shape as you get warmer. It becomes straighter. So that means the upper troposphere will warm more than the lower troposphere. That's a negative feedback because the emission height's up here in the upper troposphere. So you warm up here a given amount, and because the change of the slope, it means you warm down here by a lesser amount. So that's called this lapse rate feedback. But again, that's basic thermodynamics, and it tells you that the warming will be less than you would expect it because of the change in the lapse rate with warming. So on one you have a positive feedback because of the saturation humidity, on the other you have a negative feedback because of the lapse rate. But you also have other things going on because of what we know about water. There's two I'll mention. One is this number up here, 200 Kelvin. We claimed that the 200 Kelvin sets the concentration where water becomes radiatively unimportant. And that's going to be the same. So if your atmosphere is warming as a whole, but this temperature is staying the same, then the temperature difference between here and here is increasing in a warmer climate. If you know the slope, you can say that means the troposphere is getting deeper. But the important difference is the temperature between the top of the weather layer, the top of the tropopause, and the surface is increasing. And clouds, the greenhouse effect of clouds depends on this temperature difference. this ends up being another positive feedback. So you can just imagine this scenario. We're saying everything we know about water is the relative humidity will stay constant, the lapse rate will follow the first law of thermodynamics, and the greenhouse potential of clouds. We're not going to do anything funny with clouds. We're going to keep clouds exactly the same, and we're going to say they're just going to follow this deepening troposphere. So this is our null hypothesis. And what you would find is that the greenhouse potential of clouds depends on this temperature difference. This increases in a warming climate, and that also acts as a way to amplify change. So that's another thing. And the last thing, of course, there's a fair amount of surface frozen water, snow and ice, and as you warm, of course, that's going to melt as well. So if you put these things all together, you end up, from our understanding of water, you say this isn't the best null hypothesis because of what we know about water. The best guess, and here we did this for this paper, we went through and we went to the different estimates, and we said if we just take those things about water that we really understand, then our best guess would be that the climate would warm, instead of 1 degree, it's going to warm about 2.5 or 2.7 degrees. And there's some slop in this number, that's what this is, and it's mostly bookkeeping slop. I mean, it's sloppiness in calculations because our physical assumptions are very precise. We're saying the atmosphere is simply changing in a way that keeps the relative humidity constant, that keeps the same tropopause temperature, changes its lapse rate, everything else is staying the same. And this is something you could calculate a lot more precisely than is shown here, but it hasn't been done because people have been working about more complicated problems. But this is, I would say, the null hypothesis about how much the Earth would warm. It's really this number, not this number. So we're going to start here at 2.7. Now you can do what most people do, what my center does, what a lot of different places do, and you can say, let's build a complicated model of all of this. So here we're just dealing with understanding. But you can make very complicated models spread out over 1 million lines of computer code and run them over hundreds of thousands of processors and get different groups to do this all independently. And you'll get a complicated climate model, which looks like this is Ben's. This is what you get when you do that. So this is what you get from this I say you get from understanding what we understand about water. And this is what you get from modeling. So you try to build models of the Earth system, which have basic physical principles embedded in them, but they have a lot of things that we make up because we don't understand lots of things about the Earth system. So we say, well, the clouds are going to change, and we don't quite know, so we'll make them like this, and the trees are going to grow, or they're not going to grow, and rain's going to fall here and there. And you get complicated models. And what you find is that our understanding explains to a good degree what the models are doing. The spread in the modeling is about twice as large as the spread in the understanding, and there's a tendency of the models to give more amplification than you get out of understanding. But for the most part, what we understand about climate change here tells us that, can explain a lot of what the modeling is doing. And what I'd like to do in the last part of the talk is say, okay, I hope to convince you that what we understand about water makes us think climate change is actually a serious issue that poses real risks. And that understanding is based on very solid physical principles. But there's a fair amount of spread here. It could be even more. This is just what models do. It doesn't need. There's a lot of things we don't know about water that aren't in here. But this is our starting point. And our starting point says, well, we should take climate change seriously. But then if you get to the details and you say, well, what are we going to do? How much is it going to warm in New York? Are we going to have more hurricanes in New York or less? Are we going to have more violent storms? Is it going to be warmer over the North American continent versus the European continent? Is the Gulf Stream going to shut down? What's going to happen to the monsoon? All of these regional things end up being very, very much connected also to our understanding of water, or actually lack thereof. And one way to show that is when you look at this extra spread here, you can say, where does that come from? So people have spent a lot of time analyzing these models and trying to relate them to our understanding here. And what you find in this bar chart here is that it's a breakdown of how much uncertainty and different effects contribute to the overall uncertainty in climate change. And the only thing I want to show in this figure is this curve. This guy here is much bigger than all of the others. And it says that the changes in cloudiness dominate uncertainty in projections of future climate change. So when you take complicated models, the cloudiness can change, and depending on how the cloudiness changes, you get very different answers. So most of that additional spread that we saw here is coming from how clouds change in the climate system. And I want to try to illustrate that by an example. And I'll illustrate that by an example because with the climate system, it's very easy to get confused because there's so many interacting components, so many complex things. Does the land matter? Do the trees matter? Do all the details of how you represent carbon cycle processes, biology in the system, little dust particles, all sorts of things. And we're saying, no, everything fundamentally comes back to our understanding of water. And to illustrate that, here what you can do is you can take a very complicated model of the climate system that's shown here and make it simpler. And if it's really this base understanding of water that's underlying our uncertainty, we should maintain the same level of uncertainty as we make the problem easier and easier. So this is a complicated problem. You have an ocean that's interacting, deep ocean currents, deep water forming in the Weddell Sea or in the North Atlantic, continents, mountains, and you say, let's get rid of all the mountains. Let's get rid of the continents. Let's get rid of the tilt. And so we have a very simple water-covered planet. And we're even getting rid of the oceans in the sense that we'll just specify what the ocean temperature is. And we'll ask a very simple question of this very complicated model now. And we're going to say, let's give you an ocean with a prescribed temperature. And let's just increase the ocean temperature. What's going to happen to the clouds? So you can take those 20 models or whatever that gave you that big spread and ask them that very simple question. Here you have a rotating planet that's covered by water, nothing complicated going on, just an atmosphere, water above and the prescribed water below. And we're going to warm your surface by a few degrees. Tell us what happens to the clouds. And the answer they give you is this. And the way it's done is each one of these is a different model, and we're looking down at it. And what you're seeing here is the change in the radiative effect of the clouds. So this is, clouds are changing, say here, this is near the equator, this is near the poles in this model. And blue means that the clouds are changing in a way that actually makes the warming less dramatic than you would think, than our null hypothesis perhaps. And red means the warming is actually more dramatic than you would think. And it's happening because the clouds are changing in a way where here you might say their albedo effect is decreasing or their greenhouse effect is increasing, and vice versa here. But what you see is the models really don't have a clue. They have a bit of a clue. If you look long at this, you'll see some patterns which are robust. In the extratropics, they tend to all be orange up here from the expansion of the Hadley cell. So there's a few places where there seems to be robust behavior in how the clouds respond, because as the storms that are in the mid-latitudes retreat with the expansion of the Hadley cell, they do that in all of the models. But if you look through the breadth of the tropics, here the clouds are changing in a way that is reducing the warming. Here they're increasing the warming. This model and this model are actually the same model, but we just gave them a slightly different pattern of temperature. And so it shows you that the changes in clouds in models are fairly poorly constrained by our understanding. And so this is, again, you could say this is the things that we don't understand about water, which limits our ability to say what's happening in a future climate. The fact that the models disagree so much is why we have that large spread. It doesn't change the basic picture. That's based on firm, good understanding. I think this 2.5 to 2.7 degree warming. The question is that spread around that, and that's what you're seeing here. This is an expression of that spread. Okay, nothing here is saying that the planet won't warm. It's just saying that some models will say it's only going to warm 2 degrees, and this one will say it's going to warm 4 degrees. And that's because of the differences in how clouds are behaving. So I have a couple more slides. And I wanted to take this to precipitation, because you might think precipitation is even harder. There. Okay. There. So here I took 6 of those models for precipitation, and we did the same thing. And we asked, how will precipitation change in a future climate? And the first thing you get when you look at this is it seems almost as scary as the clouds, not quite. And what you find is that the blue means it's going to rain more, and the brown means that it's going to rain less in the climate as a whole. And what you find is, especially in the tropics, the models have very little idea or little agreement in how precipitation will change. So here you see the tropical rain bands are converging more at the equator, and here they're sort of spreading out, so you get more rain moving away from the equator. Here you see a broad increase in precipitation. Here you see increase far away from the equator. There's some robustness, again, that you see some increase in rain in the extratropics here, and some decrease of rain all the way up here. But in the tropical zones, you have really little idea of what the tropical rain bands will be doing. So you could say, and it's a good hypothesis, is that regionally you have very little idea based on the models and the constraints in our understanding of what controls the position of rain bands. You have very little idea, if you're living here, is it going to get brown or is it going to get blue? Is it going to be, this is 3 millimeters a day. The globally average precipitation is 3 millimeters a day. So it rains on average, if you're on one of the margins of the rain bands, this difference of 3 millimeters a day is about how much it rains to begin with on these margins. So you might be talking about a 50% reduction in rain, or you might be talking about a 50% increase in rain, depending on which scenario you're looking at. So you might be horrified by this because you say, well, the models know nothing about rain. But you can sometimes be a little bit smarter. Normally this isn't something that I am, but this is stolen from a co-author who was a bit smarter. And she said, well, let's not look at the rain regionally, let's just look at the rain conditioned on how a model represents the circulation. So if you go to a climate model, and you don't say, let's look at this point and say how the rain changes. We say, let's look in the space of your model where you already have rain, will the rain be increasing? Or if you don't have rain, will the rain be decreasing? And she, again, does this binning job versus the large-scale vertical velocity. So if you look at where air tends to be climatologically going up, you have convergence of moist air, and you tend to have rain already, or if the air climatologically is going down. And then you look at all those models, what you find is that, and if you focus on this black curve, is that this is the spread of the models. You get actually very good agreement about how the models are changing in terms of their precipitation. So there's a good part of this space here where you have a pretty good understanding. This is a theoretical prediction, actually, based on our understanding of water. So one of the two things we know about water and changing rain is that as you warm the atmosphere, you're going to increase the radiative flux divergence of the troposphere. So it's going to rain more. So you know that. And the other thing you know about water is this ClausiusClapeyron, how much water the atmosphere holds, so to speak, if you like to think of it that way. So if you have a given circulation, and you're bringing water in at the base, and it's going up, and then it's raining out, if you have a warmer atmosphere, you're going to be doing this of understanding, the radiative understanding of water, and the thermodynamic understanding of water together, then you get this dashed line. And what you find is all of the models agree with the theoretical prediction fairly well in these regions of the atmosphere where it's gently subsiding or rising motion. But over here, about half of the Earth, we have bigger problems. So this is a lack of understanding of what's going to happen because of water, and this is understanding of what's going to happen because of water. So that brings me to the end. I would say insufficient understanding of water explains, to a large degree, the imprecision of our estimates. So understanding gets us the sort of bullseye, the good null hypothesis, which is about 2.5 times of what we would get if we didn't understand water. But a lack of understanding or insufficient understanding of water explains most of the imprecision estimates of global changes that we have, and large deficiencies in regional projections. And the meta point here is the latter points to the need to better understand how water couples to circulation, this link between water and circulation, because if we can't understand that, there's very little that we can understand about regional climate change. And regional climate change is the key to dealing with adaptation. As the climate changes, we're going to come up with strategies to deal with it regionally. And we have to understand how the climate's going to change regionally. And we have to build that on a foundation of understanding, not just downscaling models, which give very different patterns, like I showed before. So if I could have communicated anything to you, it's this. Most of what we know about our atmosphere, climate, and climate change is tied to an understanding of water. But the important things that we don't know, and that's these globes where you saw these different pictures, are also tied to a lack of understanding of water. And so with that, I'd like to conclude and thank my sponsor, the Max Planck Society, and Sandrine Boni, who's a co-author of the paper that is this lecture is partially based on, and that was her graph there at the end. Thanks a lot.